I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount.
A negative correlation would be when variable x goes up, the values of variable x go up, the values of variable y go down. So like number of cigarettes you smoke per day, as that number goes up, so if you're a respondent and you could either smoke 0 to like 100 cigarettes a day, and then the variable y would be health, and so your health score would go down as your cigarette score goes up. Does that make sense? And then you look at each respondent, and respondent 1 smokes 20 cigarettes a day, so they're pretty high, so their health score is going to be pretty low. Does that help clarify? Then you'd say that smoking is negatively associated with good health. With part 2, the reason why I keep bombarding you with get this variable, get this information, is because for the research project, you're going to need to be able to put, here's what the variable is, here's what the question was that was asked, and here's some of the descriptive statistics on it. In any variable you're going to use in your project, you're going to need to say all that information. So it's better just to have it on a Word document, and you can build off that. And for tonight's assignment, it's going to be looking at correlations. So you can pull from variables that you've already done, so you don't have to research for that work. You can just cut and paste. Yeah?
So when we've been doing this, so we should have our question already, because I keep rotating stuff around.
So it's fine right now to just be exploring. Yeah. But you should be thinking, ultimately, what is my research question going to be, or what variables am I really interested in? I think McKay has the horoscope question. What is your horoscope? So that could be interesting to see if your astrological sign is associated with anything. It could be associated with exercise or smoking or things like that. But this isn't random. You're going to be thinking, if I was going to do a sociological research project, how would these variables fit in? And maybe I should start, as you're thinking, I want to do a project on this, you're going to want about 20 variables in the end. Not all of them are going to matter, or not all of them are going to be used, but you're going to want to have access to them. And then especially if you're doing income, you're going to want to find the right income variable, because there's a lot of them, or even the race variable. There's one race variable that only has 3 options, but then there's another race variable that includes Asian and Hispanic. So hone in on what would be good variables to use. So I'm going to touch briefly on properties of correlations before we move into the main focus of this lecture. But properties of correlation, what we covered was R is the notation for correlation, and R can range between -1 and +1. A value of 1 would be a strong positive correlation, and a value of -1 would be the strongest negative correlation. So strength is indicated on the extremes. So we have positive association is whenever R is greater than 0. So the correlation is on a continuum. So you can have a weak positive correlation or a strong positive correlation. And likewise, negative association is when R is less than 0. There's no linear association when R is approximately 0. So you might have an R of like 0.05 and you say, oh, look, there's a correlation. but really it just barely is hanging on. So there's probably not any type of meaningful relationship between the variables. So graphically, here's 3 different scatter plots, and what do each of these dots represent? So the x-axis would be variable x, let's say height, and then the y-axis would be variable y, which would be like weight. And so then what would each dot? A specific person. Yeah, it's each of your cases. And so then we see here, r is 0.7, and you can see there's, even without the line, there's a general trend in this direction. And then with this one, we have, so like we could say x-axis is health and y-axis is smoking. And so as people have high smoking scores, they have low health scores. When you plot all those points, you can visually see that it's a negative correlation, negative 0.7. Whereas this one, the dots are just kind of all over the place. This could be horoscope and education. You know, no matter where you fall on the education spectrum, the horoscope can be anywhere on that continuum. There's no association between those two. The closer r is, plus or minus 1, the stronger the linear association. R does not depend on units of measurement, so it doesn't matter like if you're measuring height, if you're using inches or centimeters, it's not affected by what units you're using. And then the correlation between x and y is the same as the correlation between y and x. It's interchangeable. One thing that you will need to be able to do is be able to look at a scatter plot and identify if it's a positive or negative correlation or no correlation. So be somewhat familiar with how these work. You wouldn't have to look at this one and say, oh, that's a 0.7, but you'd have to say it's greater than 1. And with today's assignment, you'll be going on the GSS page and it will calculate it for you. And so you'll put in the 2 variables and you'll say what's their correlation score, and it'll give you this R value. So what we've been talking about is linear associations. As x goes up, y goes up, or vice versa. If you look at this scatter plot, what's the correlation between x and y? It's a little bit of both. Okay, so it's positive and negative. Actually, if we put all of these values into the formula, what we would find is that the correlation is actually 0. And it's exactly for the reasons that Tim mentioned, is that all of the positive relationships are canceled out by all of the negative relationships. And so what you end up with is a linear correlation of 0. But is there an association between x and y? Is there sort of a trend as x moves in one direction, y moves in another direction? Yes, there is. This is the trend, but it's a nonlinear relationship. It's yes because knowing x helps you predict y. However, the association is nonlinear. So just because you get an R score of 0 doesn't necessarily mean there's no relationship. It just means there's no linear relationship. And so if you guys remember from calculus, y equals x squared, so it's a nonlinear relationship. And oftentimes, like one common example of this is, let's say x is age and y is income. When you're really young, your income is low, but then as you get older, your income goes up. But then as you get even older, like past 65, your income goes down. So that's an example of where it's a nonlinear relationship between x and y. That just kind of covers some of the basic things with correlations. And we'll move on to the main focus, which is understanding inference, and in particular, confidence intervals. Back to the big picture, we have our population here, and then we pull a sample from the population through sampling. What type of sampling do we always strive to do? Random sampling, excellent. And then from our sample, we can make inferences about the population. By taking the values in the sample, we can say this is what's true about the whole population, and that's called statistical inference. Here's 2 big terms that you need to know the difference between. The difference between a statistic and a parameter. A sample statistic is a number computed from sample data. As much as possible, I will put in sample statistics so you know we're pulling this number from the sample. It would be referenced like, what does the sample mean? It's the mean income of the people in the sample. The other is a population parameter, and it's a number that describes some aspect of a population. For example, the population mean is the mean income of the entire population. The thing that we typically have access to is the sample mean, because we pull our sample, we take all their income values, and then find the mean. And then the thing that we're interested in really knowing is the population mean, the mean income of the entire population. The core of why and how we do statistics is we really want to know the population parameter, whatever it is, but an efficient way to get to it is by drawing a sample and getting a sample statistic and then inferring from that sample what the population parameter is. These two terms are very key and they're going to be coming up throughout, and it's important to differentiate between them because you got to be thinking, am I talking about the population parameter or am I talking about the sample statistic? So it says we usually have a sample statistic and want to make inferences about the population parameter. Okay, so then there's specific notations that are used, like the little symbols, and we've already gone over some of the sample statistic stuff. So like mean is x bar, proportion is p hat, standard deviation is s, correlation is r, and slope is b, and we'll cover that later. And then for population parameters, you have mean is mu, p for proportion, sigma, rho, and beta. And so a lot of times they won't say here's the population mean, they'll just say here's mu. And you'll need to know mu refers to a population parameter and it refers specifically to the population mean. Probably the best thing is to memorize these and know these because they're just going to pop up everywhere. And so when I say x bar equals 64.5 inches for height, what is that telling me? And you'd have to say, oh, that's the sample mean height for the sample that we're looking at. Okay, so if we look at where this is played out in real world, taking from a sample and making inferences about the whole population, Gallup surveyed 1,500 Americans between June 9th and June 11th, 2012, and 49% of these people approved of the job Barack Obama is doing as president. And so the sample proportion of people who approve of Obama is 0.49. So like sample statistic is the general term, and then you want to know what statistic about the sample are we interested in. Because this is a categorical variable, either yes you approve or no you don't approve, we want to find the proportion, and so p hat is 0.49. Based on this sample of 1,500 Americans, what do you think is the true proportion of Americans who approve of the job that Barack Obama is doing? What do you think is the true proportion? We randomly sampled 1,500 people. Yeah. 49. And how confident would you be that it's 49?
Very confident. Because it was a random survey, 1,500 large.
Okay. And how many people are in the U.S. approximately? I think it's 330 million now. So they talked to 1,500 people, and then we want to make an inference about, let's say, 300 million people. Well, ultimately, we don't know the true proportion unless we interviewed everybody and asked them, but we can estimate it. And that's what we're going to be talking about, is how do you make, with sample data, a good estimate of what the population is. So then I want to differentiate between point estimates and interval estimates. So a sample statistic gives a point estimate, which is a single number for the population parameter. So similar to what Brittany was saying, what is the point estimate from that Gallup study? The single number that's put out there as the estimate. Brittany? 49, yeah, 0.49 or 49%. But usually it's more useful to provide an interval estimate, which gives the range of plausible values for the population parameter. If you just need a quick response and you want to give a very rough estimate, you can say, okay, 49% approve of him. But if you kind of want to be more precise, you can say, well, it's actually within this range. And that's what the interval estimate is. The interval estimate is the point estimate, which is 0.49, plus or minus a margin of error. And oftentimes in studies, if you look closely, you'll see what the margin of error is. They might have made a point estimate of 0.49, but what's the margin of error with that estimate? So then the big question is, how do you determine the margin of error? And that's what we're going to be moving towards trying to understand. This is from the actual Gallup website, and this is a trend. They basically ask this question like every 3 days. So you always wonder who knows what the approval rating is. Well, one of the people who does it is Gallup polls. And so you can see February '09, December '09, October 10, August 11, June 2012. And up here is the 49% approve, 45% don't approve. Why don't these numbers add up to 100? So this is a categorical variable, and so one of the categories is yes, approve, another one is no, don't approve, and there's probably a third category that people get dropped in, and what do you think it would be? Undecided or something. So even like with the GSS, it'll ask even things like race or whatever. It's either white, black, or Hispanic, but then there's probably another category called other, and those people are just as important to be included. And so technically up here it could say 4% undecided or whatever it is. But if you look at the fine print, they say right here the margin of error is plus or minus 3 percentage points. Good studies, or studies that want to be somewhat credible, will provide the margin of error. Because if this number is really big, if it's like plus or minus 20 percentage points, then what good is this point estimate if the interval estimate is so large? We can't say anything meaningful about it. But then you're probably wondering, well, how is this calculated? How do they know it's plus or minus 3 percentage points? And that's what we're going to be looking at. So you have point estimate is 0.49. The interval estimate, the point estimate of 0.49 plus or minus 0.03, which is the margin of error. And so then this gives you the interval. 0.46 to 0.52 is the interval estimate, or the range of plausible values for the approval rating. So then putting it in words, between 46% and 52% of Americans currently approve of the job that Obama is doing as president. So the point estimate is the sample statistic, and then the interval estimate is your sample statistic plus or minus a margin of error. And that's what we're going to be talking about today, is how do you calculate the margin of error? Because we already figured out how to figure out the point estimate. So the population parameter is a fixed value. For any point in time, that's always going to be the same. Like, it doesn't vary. However, sample statistics vary from sample to sample. They will not match the population parameter exactly. So like on June 11th, 2012, there was a fixed proportion of people who approved of Obama's job as president, and they did a sample of 1,500 people. The sample that they pulled from said that 49% approve of his job. So what if they randomly sampled 1,500 other people? Would that sample statistic be 0.49? Or could it vary slightly? Could it be 0.491, 0.489? The idea is that your sample will vary because it is a sample, it's not the whole population. And the thing that varies is the sample statistic. The thing that is fixed is the population parameter. Like, that just stays the same. The key question is, for a given sample statistic, what are the plausible values for the population parameter? How much uncertainty surrounds the sample statistic? Because your sample statistic, first time you do it is 0.49, but then maybe if you did it again, it would be 0.48, and then if you did it again, it would be 0.50. So how confident are you that it's going to be right around 0.49 or whatever your point estimate is? That sort of helps generate the margin of error. It depends how much the statistic varies from sample to sample. So if we did this random sample and the first one was 0.49, and then the next sample that we did was 0.20, and then the next one we did was 0.6, you'd say, wow, I'm not really confident in this point estimate of 0.49 because the samples are all over the place, even though they're all random samples. Okay, so now to make this more fun and maybe intuitive and to learn more about the world, we're going to look at Reese's Pieces. So what proportion of Reese's Pieces are orange? So the colors in Reese's Pieces, if you forgot, is yellow, orange, and brown. What proportion of Reese's Pieces are orange? So what I brought is a bag. So this is a bag of Reese's Pieces, and this is our population. And it's about 500 Reese's Pieces in this bag. And so if we wanted to find out the proportion that are orange, what is one way we could do it? Count them all. So we could take this population, and I could send you guys to the back of the room and have you just count them all. Or we could do what Chris said and do a random sample from this population and look at the sample and see what the proportion orange are in our sample, and then make an inference about the population. We're going to run our own study. So since Chris suggested it, we get to do a random sample. But I'm going to involve all you guys, because one of the things, I'll bring it over to you guys. One of the things that we look at is that not all random samples are going to generate the same sample statistic. I want you to reach in and grab 10. So, and if you grab more than 10, you have to randomly eat the 10. No, grab 10 out and pass it around. What do you guys think the proportion is? Do you think it's 33%?
No, I think it's
25%.
It's higher than that.
30%.
Okay, I'm going to do a little poll and see.
I'm going 40 to 55%.
Oh. Let's see, I'm going to write over here. Chelsea says
30.
30%, okay. Brittany, what do you said 25?
Yeah.
Chris, what do you say?
23.
Tim?
40.
40. McKay?
35.
35. And Rachel?
30.
30, okay. What we're going to do is I'm going to go around, and what you have just done is a random sample of 10 Reese's Pieces. What's the distribution of your sample? So I'll start with Tim. This column is orange Reese's Pieces, and this column is not orange. So we're only looking at orange or not orange.
5. Orange.
Okay, so we'll go 5, and then not orange is 5. Okay. The sample statistic for your sample, what's the sample proportion of orange Reese's Pieces?
Like 50%.
Yep, so 0.5. Random sample number 1. So McKay.
I have 3 orange. And
Okay.
7 not orange.
This is your sample distribution. What's your sample proportion of orange Reese's Pieces? 0.3. Okay, Rachel.
4 and 6.
4, 6. Sample proportion? 0.4. Okay, Chris.
6 and 4.
So 0.6. And Brittany?
4 and 6.
4, 6, so 0.4. And Chelsea?
4 and 6.
4 and 6. Okay, we're running this experiment, and the important distinction is these are sample distributions, and we ran 6 samples. This is our sampling distribution. So this is the distribution of our sample statistics. So big distinction. These are our independently run studies, and then this is a collection of our sample statistics. Okay, I'm going to flip through this. When conducting a study, we need a sample size. Our sample size is 10. Typically, we take only one sample, but because we're interested in knowing how much our statistic varies from sample to sample, we're going to do multiple samples. In most studies you just have one sample, but we're wanting to see how our statistic might vary from sample to sample.
Is this something that they typically only have to do? Like, say it's like the Gallup poll. They do this once, and then can they use that? Like,
Yes.
It's almost always plus or minus 3 or 7.
Well, yeah, and this will show us how you can then mathematically calculate the margin of error. But this demonstrates the mechanics behind.
Right, I was just wondering.
Yep. So each person take a random sample of 10 pieces. What is our sample size? 10. And what is our population? There's 500 in a bag. So is our population 60 or 500? Who says 60? Who says 500? So the goal is we want to know what the proportion of orange pieces in the population. So yeah, the population would be 500, and our sample size is 10. How many samples did we take? 6 samples. Tim, what is your sample distribution? 5 and 5. Your sample proportion is 0.5. And then what is the range of plausible values for our population proportion? So at least we know that with just this little study, the range of plausible values is between 0.3 and 0.6. We have great confidence that it's somewhere between there. But the margin of error, the spread, is 0.3. So it's like we don't have great confidence in a narrow interval. And then what is the mean proportion of the sampling distribution? We have the sample proportion, and then what's the mean value of all of these? It would be approximately 0.42. So that's like the center point of this distribution. So then the sampling distribution will be centered around the true population parameter. So if we did this like 100 times and we put all these dots up, this distribution is going to be centered around whatever the key thing that we need to understand today with this is the sampling distribution, and that's different from a sample distribution. Now, why they chose names that were so similar, and you might be reading in the textbook and think, oh yeah, sampling distribution, that's these things, but it's not. Sampling distribution is different from a sample distribution. A sampling distribution is the distribution of sample statistics computed from different samples of the same size taken from the same population. This is our sampling distribution. And so it's really important to know if we're talking about a sample distribution or a sampling distribution. So a sample distribution is your sample that you took of 10, and what's the distribution of values. And in the case of a sample distribution, it's the distribution of your sample values. Whereas a sampling distribution is a distribution of your sample statistics. So it's going to demand multiple samples. So in the Reese's Pieces sampling distribution, what does each dot represent? So this dot is at 0.3, and 0.3 we got from over there, and it's the sample statistic for this sample. 0.3 is brought over here to be put into the sampling distribution. So it equals one sample statistic. So the sampling distribution shows us how the sample statistics vary from sample to sample. And that's what this is showing us. Each of these is a different sample statistic, and it shows you how your sample statistic is going to vary from sample to sample. The sampling distribution is influenced by the sample size, which influences the confidence we can have in our estimate of the population parameter. So like our sample size was 10, and there's a lot of variation. Whereas the Gallup study, what was their sample size? 1,500. And so they had a much smaller margin of error. So how confident would you be that our point estimate is the true proportion of the population if we took a random sample of 2 Reese's Pieces? So here's our population, 500, and we did a random sample of 2 Reese's Pieces. I'll do it right now. And I have 1 orange. So I would say my population proportion point estimate is 0.5. How confident would you be if I only just took 2? Not very, somewhat, or very confident? Not very confident. If we took a random sample of 100 Reese's Pieces, how confident would you be? You'd be very confident, okay? Say our random sample, our sample size was 500, how confident would you be? It'd be the same thing. I mean, if your sample size is the same size as the population, then you know what the population parameter is. But the main point is, as you increase in sample size, your confidence in your estimate goes up. But also, you can't have your sample size typically be the entire population because it's too expensive to do that and not feasible. Okay, so we're going to confirm our intuition with statistics. So what's the mathematics behind this idea of the role of sample size? So with every distribution, it has a shape and it has a center. And if samples are randomly selected and the sample size is large enough, the sampling distribution will be symmetric and bell-shaped, and it will be centered at the value of the population parameter. You've seen this curve before. So you have a bell-shaped curve that's symmetric, and then it's centered around the population parameter. This right here is mu. What does mu mean, Brittany? Population mean. Okay. And it's the same type of thing. Sigma is standard deviation. So if you go out 1 standard deviation, then 2 standard deviations, what percentage of the values fall within 2 standard deviations of the mean? 95%. Again, to reiterate, the sampling distribution is different from the sample distribution. The sample distribution is the distribution of values for variable x collected from one sample, whereas the sampling distribution is the distribution of sample statistics, like p hat, collected from multiple samples. So that was the shape. Now, the thing that we're interested in is the spread. What is the thing that we use to measure the spread of a distribution? You guys remember from yesterday? Standard deviation. So standard deviation is the way we measure the spread of a distribution. To assess the accuracy of our point estimate, we need to know how much the sample statistic varies from sample to sample. So right here, we see how much it varies from sample to sample. We need to know the spread of the sampling distribution. Are these numbers really tight around the center, or are they kind of stretched out? In the Reese's Pieces sampling distribution, we generated what is the range of plausible values for the population proportion, and then we used the spread of the sampling distribution to determine the margin of error for a statistic. So if this is really spread out, what's the margin of error? Wide and high? Yes, whereas if it's tight and all the sample statistics are bunched up together, you're going to have a small margin of error. What is a standardized way to measure spread of a distribution? And that's standard deviation. We calculate the standard deviation of the sample statistic and the sampling distribution. So we've already done this. Like yesterday, we did the standard deviation for a sample distribution. So in the same way, you'd be calculating the standard deviation for a sampling distribution. And so the formula is the same. I'm not bringing up a new formula. It's the same thing, but what these denote are different. What was n when we did the standard deviation for a sample distribution? Sample size. So when we're looking at a sampling distribution, n is the number of samples taken. For our case, the sample distribution, n was 10, and then for our sampling distribution, what is n? Brittany? 6. And then x is the sample statistic for sample I. So sample 1 was Tim, and his sample statistic was 0.5. And so you put 0.5 right in there, and then x bar is the mean value for all of our sample statistics. And what is x bar? 0.42. It's the mean value of the sampling distribution. As the standard deviation of the sampling distribution decreases, as the deviation becomes narrower and narrower, the margin of error will decrease. So, like I was saying yesterday, standard deviation is a key thing to understand, but once you figure out how to calculate it, it's the same process for whether you're doing a sample distribution or a sampling distribution. Another way of thinking about it is as the variability or the spread in the sampling distribution decreases, the uncertainty in the estimate decreases. I'll show you visually how this works, but this is mathematically how you can calculate it. Again, back to the importance of sample size, and this will show visually what we're talking about. This bottom example here is a sample size of 50, whereas this is a distribution with a sample size of 200, and this is if the sample size was 1,000. What do you notice as you increase the sample size? Each of these dots are sample statistics. So as we increase the sample size, what happens to the sampling distribution? It becomes narrower. So right here it's really spread out. In fact, ours was n equals 10, and you can see it's fairly spread out. But if we increased our sample size to like 50 or 200 or 500, it would become much tighter. Our sample statistics would all be hovering right around 0.42. The shape of the sampling distribution is unaffected by sample size, so the shape is the same. It's always going to be symmetric and bell-shaped. And the center of the sampling distribution is unaffected by sample size. But it's the spread is going to be affected by sample size, and as sample size increases, the sampling distribution will decrease. Okay, with Reese's Pieces, we'll go back to our sample size. If we increase the sample size to 100, the standard deviation of the sampling distribution will increase, decrease, or remain the same. If we increase the sample size, how would that affect the standard deviation of the sampling distribution? Brittany? It would decrease, yes. I know this is like the last thing you're probably thinking about when you're coming in here today, and I can appreciate that it can be overwhelming, but we'll keep walking through multiple examples. But Brittany's right, it will decrease the standard deviation. So in order to calculate the margin of error, we calculate it using the standard deviation. And the standard deviation tells you how spread out your sample statistics are. And so when it's spread out a lot like this, so this is going to have a high standard deviation. Your sample statistic of 0.5, we want to know how confident we are that that's the true population of orange pieces. If our sample statistics are really spread out, then there's going to be a large margin of error. Margin of error is correlated with the standard deviation. So if the standard deviation is large, the margin of error is going to be large. There's an example where I can show you how this looks. So if we increase the sample size to 100, the standard deviation of the sampling distribution will decrease, and the margin of error of our point estimate will do what? Will decrease, yes. For each sample, the proportion of orange pieces will be closer to the proportion of the population and thus closer to each other. So as the standard deviation decreases, all of these point estimates are going to come in closer towards the true population. So if we increase the sample size to 500, which is equal to the entire population, what would be the standard deviation of the sampling distribution? And we plotted out all the sample statistics. What would the standard deviation of the sample statistics be? Brittany?
0.
Okay. If I gave Tim the bag and he calculated the proportion in the bag, he would get 0.3. And then if I had McKay do it and she poured it out and sampled 500 and counted the proportion, she would get 0.3. Rachel would get 0.3. And so this little dot plot would be 0.3 all the way up, and there'd be no variation in the sample statistics. And so the spread of this distribution would be 0. So for each sample, the proportion of orange pieces would be equal to the proportion of the population and thus equal to each other. So there'd be no variation. But again, we don't sample the entire population. So here's our hypothesis. Increasing the sample size will cause the standard deviation of the sampling distribution to decrease. And so we're going to test our hypothesis. So we could do it where I could hand you guys these and I'd say, okay, take 20 pieces or take 50 pieces, but there's a quicker way to do it. Okay, this is my big old bag of Reese's Pieces, and the sample size was what? We're going to rerun our experiment here. What was our sample size? 10. We're going to draw one sample, and so then the proportion says 0.7. That was like Tim's one sample, and then if we did it 5 more times, what is this graph generating? Is it a sample distribution or a sampling distribution? So this would be a distribution of sample statistics, so a sampling distribution. All of the sample statistics. So like we're drawing the sample, we get this score, and then we put it up in here. And this is giving us our sampling distribution. So then let's just say we reran this experiment 1,000 times. What do you notice about the shape of the sampling distribution? It's symmetric? Yes, exactly. In fact, the technical term for it is a normal curve. And so you can superimpose that on here. What that's showing is even with the sample size of 10, if you gather all the sample statistics, it's going to be a normal distribution. But our hypothesis was what? If we increase what? So the standard deviation for this was 0.18. We have a sample size of 10, and the standard deviation was 0.18. So then if we increase the sample size, what should we increase it to? 100? So if we increase the sample size, what do we think this standard deviation value is going to do? So if we, instead of pulling out 10 Reese's Pieces, we're going to pull out 100, what's going to happen to the standard deviation? It'll go down. It'll decrease. So we'll rerun that. This is the sampling distribution. Each of these dots represent the sample statistic from one sample, but we're wanting to see the variation in sample statistics. And so we did 1,000 samples, and we pulled out 100 Reese's Pieces every time, calculated the proportion, and then put it up here. And this is the distribution of sample statistics. And the standard deviation for this is 0.05. So when n equals 100, SD equals 0.05. So it's going down. And then also, we're getting a sense for what the true population parameter is. Like, what's the true proportion of orange Reese's Pieces? It's going to be centered around the true population. So then we'll do it one more time, and we'll do a sample size of 500. And it draws the samples. The standard deviation is 0.02. So n equals 500. So by increasing your sample size, you're going to reduce the standard deviation, which is going to reduce the margin of error in your estimate. But you got to find the balance point. You could say, well, why don't we do a sample of 100,000? Well, that's not really feasible. So what's a large enough sample size to get a small enough margin of error? And that's what you want to find is the sweet spot. 10 probably is too small. It's going to have too much of a margin of error. But if we did 500 or more, the standard deviation is going to be small enough to where we can make an estimate. So in fact, if you look at this, you have standard deviation of 0.002, and then I'm going to say the mean is 0.50, and if the standard deviation is 0.02, if I want to find the 95% confidence interval, how would I calculate that? If I want to know 95% of our sample statistics fall within this range, how would I calculate that? If we have a mean of 0.5 and a standard deviation of 0.02. Brittany?
You're going to multiply the standard deviation by 2, and then you're going to add that to the mean, and then subtract it.
Okay, so 0.5 plus or minus 2 times 0.02, so 0.04. So 0.54 and 0.46. So we'll test this. So is it above 0.46 and values below 0.54? What this shows you is the confidence interval that 95% of our sample statistics, so if we did this experiment 1,000 times, which we simulated here, 95% of the sample statistics would fall within this range. And so that's our confidence interval, that we're 95% confident that the true population parameter is within that range. We recognize that, yes, there could be that 5% of the time where you just get a really random distribution in your sample, but we can be 95% confident that the sample statistic will fall within this range. So this is our range, 0.46 to 0.54. So if we wanted to know the margin of error, what is our point estimate, our best estimate of what the population parameter is? Brittany? 0.5. Okay, and then what's the 95% confidence interval? Is 0.46 to 0.54. So if we wanted to know the margin of error for our point estimate, what would it be? Our point estimate is about 50% plus or minus 0.04. So you can see we're using the standard deviation to ultimately calculate the margin of error. This is just one example of how you go about doing it, but hopefully you can see what's going on. We'll move on to confidence intervals, which we've started to cover. A confidence interval for a population parameter estimate is an interval computed from sample data that will contain the true population parameter for a specified proportion. Oh my gosh, it's horrible. It's true, but so a confidence interval for a population parameter estimate, population parameter, is an interval computed from sample data. In our case, it was computed from these 6 samples that we did that will contain the true population, so that's again the true proportion of orange pieces, for a specified proportion of all samples. Probably the best way to do this is to go back to this example. This is a collection of sample data, the sample statistics, and we want to know the confidence interval. Like, how confident are we that 95% of the sample statistics will fall within that interval? And that's what we calculated up here. You have to specify, would you want to be 95% confident or 99% confident, or your confidence level will determine what your confidence interval will be. The success rate, i.e. the proportion of all samples whose intervals contain the true population parameter, is known as the confidence level. Oftentimes, we'll use a confidence level of 0.95 or 95%, but the confidence level indicates how confident we are that our interval contains the population parameter. Again, we just do typically one sample statistic, and how do we know how accurate that sample statistic is? The way we find that out is, well, let's do it 1,000 times and see how much that sample statistic varies from sample to sample, and you get the distribution. Where do 95% of the values fall? They fall within a range. Like in this case, the range is 0.3 to 0.6, and it's a very large range, whereas when we increase the sample size to 500, the range was 0.46 to 0.54. So we're wanting to close that range down. Here's how it would look. Mu is mean age, and so this is the true population parameter, and it's fixed. It doesn't change. So then we do a random sample of people and get their heights, and then we get a sample statistic, which is, in this case, slightly less than the true population. And this would be the confidence interval of this particular sample statistic. So the confidence interval is xi plus or minus 2 standard deviations. So xi is the sample statistic plus or minus 2 standard deviations. And this is an important note. The standard deviation used to calculate the confidence interval is the standard deviation of the sampling distribution, not the sample distribution. So in order to calculate confidence interval, you need the standard deviation of the sampling distribution. I encourage you, after lecture, go back and read through the notes and be like, okay, when am I talking about sample distribution and when am I talking about sampling distribution? Yeah.
Does that mean that it's random?
So it's random in that the sample statistic is going to be slightly different. The confidence interval will shift. It'll be centered on the sample statistic. Right here we ran 100 more experiments, and so this time the sample statistic was right here. So the confidence interval is going to shift a little bit because each sample is going to generate a different statistic. So if we ran it 100 times, here's the sampling distribution. It's the collection of all these sample statistics. Then we can say 95% of the sample statistics fall within this range. We see 2 samples had sample statistics that fell outside of this confidence interval. And so that's expected. You're going to have sometimes the sample statistic that you generate is going to fall outside. That's why they say a margin of error. 95% of your statistics are going to fall within this range, but there's going to be some that won't. So confidence intervals, we have the standard error. The standard error of a sample statistic, this is like Tim's sample statistic is 0.5, is the standard deviation of the sampling distribution. The standard error of a sample statistic is the standard deviation of a sampling distribution. So standard error is just a special term they use when you want to know the standard deviation for your statistic. You want to know how much it varies. They call it standard error. And mainly so that you can know that we're talking about the standard deviation of the statistic versus the standard deviation of the sample. It's confusing, but a key thing to know is when we're talking about standard error, it's letting you know the standard deviation of the sampling distribution. It's confusing because you're calculating standard deviation for 2 things. So on one level, I could say, what's the standard deviation of this sample distribution? You would tell me the spread of these values. But then in this case, what we're asking for is what's the standard deviation of the sample statistics. Like, so if we ran the study 1,000 times, we'd generate 1,000 sample statistics, which is another distribution, and we're wanting to know the standard deviation of this distribution. They call that standard error. I would say it's highly confusing because you're like, first of all, I never knew what standard deviation was to begin with, and now you're wanting me to calculate it for this type of thing and for this type of thing. So it's an attempt to sort of differentiate. So confidence interval is what we did, sample statistics plus or minus 2 times standard error. And so basically, we got through all of this. I'll give you guys an assignment. We're just going to keep hammering away at this until it sinks in. This is what we're calculating. But it's mainly to figure out what's the confidence interval of our sample statistic. We're all done.